Hello, ladies and gentlemen. Welcome to Kemet's presentation titled Ripple and Transient Response of Power Supplies as part of Kemet's Design It Day. My name is David Adib, and I am Kemet's Senior Technical Marketing Engineer here in Florida. Our presenter today is Ron Stull, and he works for CUI Inc. as a Power Product Marketing Engineer. With that said, I will turn it over to Ron to give us some more background about himself and begin his presentation for today. Ron?
Thanks, David. Welcome everyone to Kemet's Design It Day. As David said, I'm Ron Stull, Power Product Marketing Engineer at CUI Inc. We're a producer of AC/DC and DC/DC power supplies up to 500 watts, and our products cover the medical, industrial, and ITE industries. We specialize in the customization and branding of external desktop and wall mount adapters. I've been with the company for 11 years, holding a variety of roles, including application support, test engineer, power supply designer, and now power product marketing, where my job is to teach fellow engineers about power supplies and their applications. Today, I'll be speaking to you about ripple and transient response, two key behaviors that are important to understand when designing or selecting a power supply for your application. I'll go over what they are, what causes them, how to minimize their effects, and how to properly measure so you can be confident in your results. So, what are ripple and transient response, and why are they important? Well, if you're unfamiliar with power supplies, you might assume that the output is a perfect DC voltage and not affected by changing loads. You may even be reassured when you measure the output of the power supply with a multimeter and see a solid, unwavering value. However, if you were to look at the output with an oscilloscope, you'd see something like that which is shown in the scope to the right. And you'd realize that in fact, the output is not a perfect DC, but will be affected by changing loads. Power supply companies such as CUI characterize these behaviors and specify them in their data sheets as ripple and transient response. So if we take a closer look at the two scope images from the previous slide, which are showing ripple on the left and transient response on the right, you can see that the ripple is how we characterize the steady state AC content on the output. It's a constant component that's always there and is an inherent attribute of a power supply. As you can see from the scope image on the left, the ripple appears as a high frequency pulsing on the output voltage. The transient response, on the other hand, is how we characterize the output's behavior due to a sudden load change. Power supplies can't react instantaneously to changing loads, and this leads to dips or spikes when the load is changed. The image on the right shows the output voltage in blue on the top and the load in magenta on the bottom, and you can see that the output voltage temporarily dips down when the load increases and temporarily spikes up when the load decreases. Both of these behaviors can be critical depending on the application. For example, having a large ripple on an analog circuit can cause reference and measurement errors, while in a motor application, which tends to have large transient currents, a voltage spike caused by one of these load changes could potentially cause an error and damage other circuits that are powered from the same rail. Some especially sensitive applications, such as memory and processors, may be so sensitive that they may have specific limits on the amount of ripple and transient that they can handle. So as I said, the ripple is an inherent aspect of a power supply, so we're going to take a look under the hood and see what causes it. We'll start by taking a look at the ripple voltage on an old linear power supply, the schematic of which is shown on the right. Now, the way a linear power supply works is an AC input is applied to a line frequency, that is a 50 or 60 hertz, transformer, which converts the high voltage AC input into a low voltage AC output. Next, a rectifier reroutes the output current into one direction, blocking the negative portion of the AC signal and instead flipping it positive. The result is that the output signal is the absolute value of the AC input signal, which you can see in the middle graph below the schematic. Finally, a large capacitor is placed across the output to hold the output voltage at the peak rectified voltage. The load will then discharge this capacitor and create a ripple on the output, as you can see on the graph to the right. Because the capacitor is across the output, the ripple voltage is the output capacitor voltage, so much of the conversation will center around this capacitor. If we take a closer look at the rectifier and capacitor voltages, we can see what causes the ripple. When we first turn the power supply on, the rectifier's output voltage charges up the output capacitor to the peak of the rectifier output. When the rectifier voltage falls, the capacitor remains charged and holds the output voltage at this peak level. However, any load that is applied will be supplied entirely by the capacitor as long as the rectified voltage is below the capacitor voltage. Supplying the load causes the capacitor to discharge and the voltage to decrease. The voltage will continue to fall until the rectifier voltage comes back up. And once it reaches the capacitor voltage, it will recharge the capacitor and bring the voltage back up to the peak again. The cycle repeats at the frequency of the rectified voltage and creates the voltage ripple, which is measured in volts peak to peak. So a few items to take away from this are, first, the ripple is caused by the charging and discharging of the output capacitor. Next, there's a load dependence on the ripple magnitude. A larger load will cause the capacitor to discharge faster and the voltage to dip further before it's recharged in the next cycle. And last, the higher the frequency of the rectifier, the less time that the capacitor must supply the load current, which will reduce the amount the voltage falls and therefore the peak-to-peak voltage of the ripple. Now, there are many issues with a linear power supply, including efficiency, size, and weight, that make them undesirable today. And so for the most part, these have been replaced by switching power supplies. And while they operate in very different ways, when it comes to ripple, it's still the charging and discharging of the output capacitor that causes it. So now we're going to take a look at how a switching power supply works and where the ripple comes from in one of those. We'll do this by looking at a buck regulator. A buck regulator is a step-down regulator, meaning that the output is always lower than the input. And the way the circuit works is this. On the left side of the circuit, we have a switch connected to Vn. The switch turns on and off at a high frequency to create a square wave from 0 volts to Vn. The square wave is applied to the node connecting the switch, inductor, and diode, which we call the switch node. This feeds into an inductor followed by our output capacitor and load, which form a low-pass filter. The low-pass filter blocks the high-frequency square wave from getting to the output and ideally only lets the average or DC value in. The average value can easily be calculated as the average amount of time that the switch is on, which is equal to the on time divided by the total switching period, times the input voltage. So, for example, if the switch had equal on and off times, the average voltage of the square wave that is applied to the filter would be half of Vn. The ratio of on time to the total period is known as the duty ratio, and in the case of the buck, it is also the output to input or conversion ratio. You can see in the second equation that multiplying the input voltage times the duty ratio will give us our output voltage. So, by controlling the duty ratio, we can control the output voltage. This is known as pulse width modulation, or PWM. For example, if I wanted to step down from 12 volts to 1.2 volts, the duty ratio would be 1/10. So, how does this lead to output ripple? To see where the output ripple comes from in a switching converter, we need to look at the current in an inductor, and to do this, we'll break up the circuit into on time and off times. During the on time, the switch is closed, which means that Vn is applied to the switch node. This reverse biases the diode and applies Vn to one end of the inductor. The other end is connected to Vout, and we therefore have a constant voltage applied across the inductor equal to Vn minus Vout. Applying a constant voltage to an inductor causes the current to ramp up at a linear rate that is equal to the voltage applied divided by the inductance. By multiplying this by the on time, we can calculate the change in current that has occurred. After the switch is ramped up for the desired on time, the switch will turn off. Now there's nothing holding the switch node and it's left floating. But because the current in an inductor can't change instantaneously and it wants to release its stored energy, the switch node swings down until the diode forward biases and clamps the switch node to ground. This means our inductor now has 0 volts on one end and Vout on the other, making the voltage across the inductor equal to negative Vout. In the same way that during the on time the current ramped up, the current will now ramp down at a rate equal to negative Vout over L. And we can determine the change in current by again multiplying the ramp rate by the off time. So let's look at the switch node and inductor current waveforms. You can see on the right that we have our switch node voltage on top and our inductor current on bottom. When the switch turns on, we have Vn on our switch node, which causes the current to ramp up, and when the switch is open, we have 0 volts and the current ramps down. This is called the inductor ripple current. And under steady state conditions, the amount that the current ramps up is the same amount that it ramps down in the off time. This essentially means that the amount of energy stored in the inductor during the on time is expended during the off time. And if you do the math, you'll find that this condition is satisfied in a buck converter when V out over V in equals the duty ratio. So this ripple current is flowing through the inductor to the output, but our output is only taking a DC current. So what happens? The average value of the ripple current, the DC portion, which is at the center of our ripple current, goes to the load. The portion of the current that does not go to the load, the AC component, goes to the output capacitor. Here again, we have the inductor current shown in the top graph, and if you subtract the load current, I out, from the inductor current, you'll end up with the capacitor current in the bottom graph. Whenever the ripple current is greater than the output current, the excess is dumped into the capacitor, which causes the voltage to rise. And whenever the ripple current is less than I out, the capacitor current goes negative, meaning that the capacitor is supplying the load current, which causes the voltage to fall. This is very similar to the linear case we just discussed, where the capacitor is charged up during one part of the cycle and then supplies the load and discharges in the other portion. But instead of being fed by a pulsing voltage, it's a pulsing current which is charging and discharging the capacitor. Now, due to the large currents and high frequency that we're dealing with in a switching converter, the actual ripple waveform is a little bit more complicated than our linear power supply example. We can't simply look at the capacitor as a capacitance by itself. Instead, we must also consider the effective series resistance, the ESR, and the effective series inductance, the ESL. All three elements are in series, and therefore the ripple current flows through all three the same, and we can easily break up the ripple into individual components. The ESR is the easiest. It's simply equal to the ripple current times the ESR and produces a triangular waveform similar to the ripple current. The voltage due to the capacitance is proportional to the integral of the ripple current, and because of the linear ramp, this results in a squared value in a round parabolic shape. And for the ESL, in the same way that the square voltage created a linear current ramp through the ESL will cause a square voltage. These three components can be summed to obtain the expected ripple. Here's an example of a buck converter ripple output, and in this one you can very clearly see those components on the ripple waveform. Now, in addition to the ripple itself, there's often noise on the ripple waveform. This is due to the high-speed switching inside the converter. When the switch turns on and off, it has to do so very fast. However, as it does, it's still conducting the ripple current. For example, when the switch turns off, we're at the peak current, and the current on the switch must rapidly fall from the peak down to zero. This causes a very large current slew rate, or dIdt, which induces voltages in the parasitic inductances. This includes everything from leakage inductance to the inductance of the leads of the switch itself, and even the traces in the PCB. In addition to the inductances, there are also parasitic capacitances, which together form a resonant tank and result in high-frequency ringing. You can see in the image of the switch node here that we have a large spike on each edge, in addition to ringing that is a much higher frequency than the converter. In this case, we were switching at about 375 kilohertz and have a ring frequency of about 100 megahertz. Now, this may not seem like a big deal since the switch node leads into a low-pass filter. However, if we look at the high-frequency model of our low-pass filter, with parasitic inductances and capacitances shown, we see that the inductor has a parasitic capacitance that at high frequency will effectively short out the inductor. And in the capacitor, we again see the ESL, which will dominate at high frequencies and block noise from being shunted to ground. The result is that our low-pass filter has become a high-pass filter, and the switch noise passes through to the output. Depending on the conditions, this may lead to the noise overshadowing the ripple. Here we see a ripple waveform where the noise was much greater than the ripple, to a point where it's hard to tell how big the ripple really is. So in data sheets, power supply companies such as CUI usually combine these into a single ripple and noise value measured in volts peak to peak. So now let's take a look at transient response and see how power supplies respond to load changes. Again, the discussion starts with ripple current. What happens to the ripple current when the load changes? In the graph, you can see that starting from the left, we have a nice constant ripple current shown in the middle. Our output, shown at the bottom, is steady and the pulse width at the top is constant. Then the load changes. In this case, the load changed during the off time. During this time, we can remember that the current is ramping down and at some point will fall below the output current, which means that the capacitor is supplying the load. Now the load is increased significantly, and instead of a small dip caused by the ripple, there's a much larger drop in the output voltage as the capacitor supplies even more current. When the switch finally turns on again, it must stay on for a longer amount of time in order to ramp the current up to the new level, meaning that the ramp up is greater than the ramp down, causing the DC level of the ripple current to increase. When the ripple current reaches its new steady state operating point, it begins to supply the load again and recharge the capacitor until finally it returns to the normal operation voltage and the duty ratio comes back to the normal value. So how do we measure or judge the performance of a transient response? Well, ideally, when the load changes, the output would remain constant and we wouldn't notice the load had changed at all. However, we know the output is not ideal, and therefore we want to know how much the output will deviate from nominal when there's a sudden load change. And second, we want to know what the response time is. How long will it take for the voltage to get back to nominal again? We don't want the output to deviate any longer than we can help. Some devices, such as high-performance processors and FPGAs, will detail specific requirements for transient deviation and response time. For example, the datasheet for one of Intel's processors specifies a nominal voltage range of 1.65 to 1.8 on one of the power rails. However, during a transient, they allow the voltage to go up to 1.95 for a maximum of 5 microseconds. So to control this behavior, the performance of the response, negative feedback is used. The feedback measures the output voltage and compares it to a known reference and then amplifies the difference. This error voltage is then fed into the PWM controller, which will adjust the duty ratio to try and keep the output voltage equal to the reference voltage. If the output's too high, the duty ratio will decrease, and if it's too low, the duty ratio will increase. So if we think back a couple slides, when the load increased and the output voltage dipped, this dip will be sensed by the feedback loop, causing an increase in duty ratio. This will ramp up our ripple current to the new level and recharge the capacitors, bringing up the output to the nominal voltage. Once the voltage is back where it's supposed to be, the feedback returns the duty ratio to its steady state value. The last part of the feedback is the compensation network. When added to the control loop, the compensation allows the designer to adjust the shape of the response. The two key aspects of this are the loop bandwidth and the phase margin. The bandwidth is important because it and the output capacitance are responsible for the transient deviation. As long as the ESR is much lower than the output capacitor impedance, the output impedance of the power supply can be estimated as the impedance of the output capacitor at the bandwidth or crossover frequency. So, because of this, in order to estimate the deviation due to a load step, we simply need to use Ohm's law and multiply the current step by the output impedance. From this, we can see that the deviation is determined by both the bandwidth of the control loop and the output capacitance. While it looks as though you can just increase the bandwidth to get the desired response, there are limitations. In general, you shouldn't set it at more than 10 to 20% of the switching frequency, and certain topologies such as the CCM boost and flyback have other characteristics that limit the bandwidth, such as a right half plane zero. So the choice in topology and the switching frequency both directly affect the transient deviation performance. The response time, on the other hand, is controlled by something called the phase margin. It relates to the dampening factor of the step response. An underdamped response will be fast, but will overshoot and can oscillate. An overdamped response will be slow, but will not overshoot. And a critically damped system is right in the middle, achieving a fast response without overshoot or oscillation. A phase margin of around 60 degrees gives close to a critically damped response. A lower margin will become less damped, and more margin will tend towards overdamping. So now that we know what they are and what causes them, how can we reduce or mitigate these attributes? As we discussed at the beginning, the ripple is due to the ripple current flowing in the output capacitor, while the noise is due to fast switching and parasitics within the supply. Each is handled a little bit different than the other. So when attempting to reduce the ripple and noise, it's helpful to look at the waveform and understand the different components. That is, what part is noise, what part's due to ESR and ESL, and what's due to the capacitance. By understanding this, you can more effectively mitigate it. In some cases, it's the noise that dominates. For example, in the image on the left, we see that the noise is the obvious dominant component. We can significantly reduce the peak-to-peak magnitude by getting rid of this noise, and in general, noise is easier to reduce than ripple. Because it's a much higher frequency than the ripple, a little extra capacitance or a small LC filter could be used to filter out some of the noise. If designing a power supply, you could reduce noise by paying close attention to the layout and minimize parasitic inductances by keeping current loops small. This could also be reduced by switching components, such as MOSFETs, to a different package with a lower inductance. Switching from a TO220, for example, with long leads to a leadless DFN package would reduce the added inductance that package leads contribute. You can also try and attack the noise at the source by adding snubbers or clamps to the switch node to reduce the switching spike and reduce oscillations. However, the ripple image on the right looks like the ESR is the dominant component. We can tell this by the triangular nature of the waveform. The capacitive component can barely be seen due to this large triangular shape. So in this case, we might start by trying to reduce the ESR, which could potentially be done by switching to a low ESR capacitor or paralleling multiple capacitors. The ESR, like ESL, is also influenced by the package and layout. Reducing lead length and minimizing the loop created by the layout will help reduce the ESR and ESL effects. So now, how do we improve the transient response? Internally, we can do this by modifying the control loop. As we discussed earlier, the bandwidth and output capacitance are directly related to the peak deviation, and the phase margin is related to the response time. By adjusting these, we can tune the response to our needs within the limits of the chosen topology and powertrain. For the user of a power supply, as opposed to the designer, we have limited options. Essentially, the only option we have is to increase the capacitance. ESR and ESL should also be minimized so that they don't factor in. It should be noted that there's a limit to the amount of capacitance that may be applied to the output of many power supplies. Typically, if too much capacitance is applied, it can send the power supply into overcurrent protection on startup, as the capacitors represent a short initially. They're also part of the control loop and can affect stability, so care should be taken when adding bulk output capacitance. On a system level, how the load is connected can also influence the response. Any inductance or resistance between the load and the power supply can affect the response. Inductance will slow it down and lead to a larger deviation and potential oscillations, while resistance of the load connections can lead to a large DC offset between the loaded and unloaded condition. This will need to be factored into the overall deviation and may mean that the transient dip or spike must be reduced more than it would be otherwise. So last, we're going to talk about how to measure ripple and transient response. Without being able to accurately measure, you won't know if you're meeting your requirements or not. We've talked a lot about parasitics, especially inductances, and how they cause noise and other detrimental effects, and with probing it's no different. In order to get an accurate measurement, the inductance created by the probe needs to be minimized, and this means ensuring a small loop. When using an oscilloscope, it's tempting to use the hat and gator clip leads that come with the probe. However, these lead to a large loop like that shown in the top image. This can amplify the ripple and noise and even pick up external noise. And to avoid this issue, there are a few common probes. The first is the paperclip method, shown in the middle image. It's called this because a paperclip, or some other conductor, is wrapped tightly around the probe ground and the hat is removed to expose the probe tip. This forms a small loop area between the probe tip and the return through the paperclip and can easily be applied across a component on the output, such as a ceramic capacitor. The next method is the tip and barrel method. This method doesn't require any external parts like the paperclip. Instead, the sleeve is removed from the barrel and the barrel is applied to ground directly. This method can be a little tricky as there's not always a good location to make a connection of both points. The last and best method is to use a 50 ohm cable, such as a coax, and solder it directly to the output. The probe is then terminated at the scope with a matching 50 ohm impedance. This method requires a DC blocking capacitor between the signal and scope, but will give you the best signal quality. Often, when measuring ripple and transient, you're measuring it against a specified limit. In order for the measurement to be meaningful, the condition of the measurement must be specified and matched for a comparison to be valid. For ripple and noise, there are typically three conditions that will affect the result. The first is the bandwidth of the oscilloscope. Most power supply manufacturers specify a scope bandwidth limit of 20 megahertz. This can usually be set inside the scope settings and gets rid of the high frequency noise that may be radiated from other devices in the area, such as test equipment or fluorescent lighting. The next item to note is that most manufacturers also characterize the ripple and noise with two capacitors added to the output, a small, typically 100 nanofarad ceramic capacitor and a low ESR electrolytic are usually specified on the order of 10 to 47 microfarads. And last, you should be sure that you're performing the measurement at the same load that is specified in the datasheet, which is typically full load. For transient response, it's important that the transient load conditions are paid attention to. While mathematically we may look at a step response with a sharp vertical edge, actual transient loads will have some ramp between the two load states. This is known as the slew rate and is the dIdt, or rate of change of the current, often measured in amps per microsecond. The slew rate directly impacts the response of the circuit and must be matched for comparisons to be valid. In addition to slew rate, the magnitude of the step is important. As we discussed earlier, the change in current is directly proportional to the magnitude of the deviation. Beyond just the size of the step, its location is also important. Power supplies can behave differently between light load and full load, and transitioning from 0 to 50% may react differently than stepping from 50% to 100%, even though the delta is the same. The test setup also affects the measurement. Added inductance between the load and the power supply will negatively affect the result. Cabling should be made as short as possible and wound as a twisted pair, that is, plus and minus outputs wound together to minimize the loop area between them. DC resistance in the line can also cause a DC voltage offset between the high and low load, as shown in the image on the right. Here, it looks as though the transient deviation is actually less than the DC offset caused by the load change. This may be due to long output cables. Here's an example of the effect that test setup can have. The left image here shows a transient response measurement made with cables that were too long and not wound together. You can see the current on the bottom has a round edge and overshoots the upper load point, causing a larger current change than intended and thus a larger transient spike. This is compared to the image on the right that has sharper edges with no overshoot and was captured with improved connections. It also looks like there's been a slight reduction to the DC offset between the two. It's also had an effect on the shape of the response. We see that the shape is a little different with the slew rate corrected. So, in conclusion, ripple is caused by the charging and discharging of output capacitors as a result of the ripple current flowing through it. The transient response is due to a mismatch between the DC level of the ripple current and the load current and the time it takes to respond to it. Both are directly affected by the output capacitance, but ESR and ESL and other parasitic circuit elements will also have an effect and must be taken into account. For an accurate measurement, requires attention be paid to probing and test conditions, and the test setup should minimize inductances and DC resistance between the power supply and load. For a deeper dive into these subjects and into power supply design in general, I would recommend these references, which were used in putting together this presentation. And that's all I have today. Thank you for attending Kevin's Design It Day and for taking the time to listen to our presentation.
Thank you, Ron, for this informative presentation. Thank you to all of our audience today for watching. I wish you all a good day. See you next time, and goodbye.